You're welcome to the chapter where we will be combining everything we did in the second part of the course and even in the first part of the course. We will be dealing in this chapter with cross-sections that are subjected not only to double bending but also to torsional moments, shear forces in both directions, and concentrated normal forces. So we're going to be dealing with sections with more than one loading acting on the section. Right? So you're going to see sections where you're going to have double bending with a torsion, double bending with a shear force, double bending with a shear force in both directions, and a concentrated tensile force and a torsional force. Everything we have discussed we're going to put in one cross section, all right? And you're going to see how to calculate stresses at any point on the cross section due to the combined effect of all what's happening on the cross section. Now, everything we have discussed so far, so recall that we have said that the normal stress at a point, all right, which is sigma at a certain point on the cross section, all right, is what's happening due to the force, which is sigma force, plus what's happening due to the bending moments, all right? And we have explained that in chapter 6, where we put sigma is equal to sigma force plus sigma bending, all right? And it's equal to plus or minus P over A, which is the sigma force, plus or minus mxy over ix, plus or minus my x over iy, given that the coordinate system was y and x. Alright, so this is the first principle of this chapter, is that if you want to calculate the normal stress at a certain point, it's equal to what's happening due to the force plus what's happening due to the bending moments. And we have done a lot of exercises on this concept. And so far in chapters 5 and 7, we have concluded that what's happening due to shear, right? So what's happening in shear, so shear stress, which is tau at a certain point, is a combination of what's happening due to the force plus what's happening due to the torsion. Very important. Bending moments create normal stresses. Torsion creates shear stresses. And the shear stress at a certain point is equal to what's happening due to the force. Right? So and here tau at a certain point is tau force plus tau torsion. Alright, remember this, we're going to use it a lot. Even that one, I use these two a lot. And tau force is VQ over IT. Alright, plus or minus tau torsion, which is T rho over J. Right? So the combined effect of normal stresses is what's happening to the force plus what's happening to the bending, which is plus or minus sigma, plus or minus P over A, plus or minus mxy over ix, plus or minus myx over iy. And what's happening due to the shear is a combined effect of what's happening due to the force plus what's happening due to the torsion. All right? And tau force is VQ over IT, tau torsion is T rho over J. Okay? This is it. This is combined loadings. You will be asked to calculate both normal and shear stresses at a certain point when the cross section is subjected to more than one loading. All right, so this is the objective of this chapter. The objective of this chapter is calculate normal and shear stresses. Calculate normal and shear stresses. All right, at points on a cross section, right, subjected to combined loadings. For example, you might be having a section like this, subjected to a bending moment. Let's say this is y and this is x, mx, my. You might have a force in here, you might have a shear in this direction, Vy, you might have a shear in the other direction, Vx. And you might have a torsion like this, T or MZ. So if I ask you to calculate the stress at this point or the stress at this point, how would you do it? This is what we're going to learn. A step-by-step procedure on calculating both the normal and the shear stress at certain point on the cross-section, given that it is subjected to combined loadings. Okay? Now I'm going to give you a step-by-step procedure on how to do that through an example. I'm going to give it to you through an example. So, suppose that you have a sign. Okay? This example you get a lot, and you can actually see it in reality. You have a sign or a type of sign on the streets, right? And you have on the sign, okay, you have the weight of the sign, which is going to be acting at the centroid. Let's say it is 100 kilonewtons. Okay. Let's say we have the force that's coming from the wind, okay, which is acting in this way, like this. So let's say that this F is 70 kilonewton. You're asked to find the shear stress at these 2 points in here, so point B and point A on the bottom of the column that is holding the sign. So you have a sign subjected to a wind force of 70 kilonewton acting into the page, weight of 100 kilonewtons, and you're asked to calculate the normal and the shear stresses at points B and A at a section lying at the bottom of the cylinder that is holding the sign. What do you do? How do you solve this problem? The first thing that you should do, the first thing, which is step 1, specify a coordinate system. Specify a coordinate system. The first step in these types of exercises, you're going to be facing these exercises a lot, right? And you're going to solve a lot of examples. And the first step should always be, step 1, specify a coordinate system, meaning an X, Y, Z coordinate. Alright? Specify a coordinate system, an X, Y, Z coordinate. So for example, I'm going to tell you that let's say that this is the Y axis, this is the Z axis, and this is the X axis. It will help you a lot, trust me. So step 1 is specify a coordinate system. Alright? After you specify a coordinate system, step 2 is going to be draw the cross section. So step 2 in here, draw the cross section, draw a cross section containing the points that you are interested in. Alright? Now, we're interested in calculating the normal and shear stress, so I forgot to tell you that the question is calculate tau A, tau B, sigma A, and sigma B. Alright? So after we specify a coordinate system, we draw a cross section containing the points that you are interested in. So we want to draw a cross section of this thing in here. Okay, where B is at the bottom and A is at the left. So this is obviously a circle. Alright? It's a circle of diameter 10 millimeters, where the radius in here is 5 millimeters. And according to our coordinate system in here, if we take our coordinate system and copy it to the bottom plane of the cylinder, you're gonna have the X, so you're gonna have the X in here like this. This is gonna be the Z, and this is gonna be the Y. You agree? X, Y, Z, and Y. Alright? So if you're doing a cross section of the plane that contains A and B, the x-axis is going to be directed downwards, and the z-axis is going to be directed to the right. And point A is going to be lying in here, and point B is going to be lying in here. Do you agree? So if you get the coordinate system that you chose, drag it and put it at the plane of interest, which is the plane that contains your points of interest, A and B. if you want to draw the cross section of that plane, all right, meaning that you're cutting the cylinder and seeing its cross section, you're gonna see that the x-axis is directed downwards and the z-axis is directed to the right, right? And that point A is to the right and point B is is at the bottom. Right? Now, after you draw the cross section containing the points that you are interested in, what you do is you want to represent all the forces on the cross section. Okay? You want to represent all the forces on the cross section. So what you do in here is step 3. Step 3 is to represent all the forces on the cross section by simply dragging them to the plane of interest. And what I mean by this is, so I'm going to ask you a question. The force of 100 kilonewtons, which is coming from the weight, in which direction is it acting? Z direction, X direction, Y direction. It's acting in the Y direction, right? And is it acting in the positive Y direction or in the negative Y direction? Obviously, it's acting in the negative Y direction. That's how you think. So you say that W is acting in the negative Y direction. That's how you think. So W is equals to 100 kilonewton is acting in the negative Y direction. Negative Y direction, as a result, what you're going to do is you're going to drag this force and put it on the cross section of interest. How are you going to do that? If W is acting in the negative Y direction, how should you represent it on the cross section? Since the Y axis doesn't appear on the cross section, then W acts as a compressive force because it's acting into the page, right? Very important. So the Y direction, since the Y direction doesn't appear on the cross section, because as we saw, only the X and the Z axes appear on the cross section. So since the W direction doesn't appear on the cross section, this means that W is either acting as a compressive force or as a tensile force. So it's acting either as a compressive or tensile, meaning it's a normal force. It's a normal force. Okay. But W is acting in the negative Y direction, and since it's in the negative Y direction, meaning it's acting downwards according to our sign convention, so acting downwards, this means it is it's causing compression. And how do we represent it on the cross section? We're gonna present it like a cross, okay, where the cross that you see in here is W equals to 100 kilonewtons. Okay, so we drag W and we put it on the plane of interest. It's acting in the negative Y direction. This means it is causing compression on the cross section according to our chosen coordinate system, X, Y, and Z. We still have the force that's coming from the 70 kilonewton. We look at the force and we ask ourselves, in which direction is it acting? X, Y, or Z direction? It's acting in the X direction. Specifically, it's acting in the negative X direction. So we go in here and we reason that F is equal to 70 kilonewton is acting in the negative X direction. So we go to the cross section and we see where the X direction is. The positive X is directed downwards. This means that F is going to be like this. It's a shear force. It's a vertical shear force. So here we have F is equal to 70 kilonewtons. Alright, this is step 3. So after you specify the coordinate system and draw the cross section with respect to the coordinate system that you specified, you drag all the forces that is coming from the system to this plane by reasoning in which direction does the force act with respect to the coordinate system that you chose. Okay, for example, here F equals to 70 kilonewtons acts in the negative x. You simply go and on the cross section we put it as in the negative x direction. W is in the negative y. Since y doesn't appear on the figure and y, the positive y convention is as chosen, then W is acting in compression. Okay? This is step 3. I told you something, however, in chapter 6, I remember. What is the price you pay when you move the load from one point to another? Because in here we're moving the load. We're moving the force W from where it acts to the cross section that you are interested in. And what is the price we should pay? The price we should pay is you should include the moments created by this force about all axes. Very important point. Very important point. So in step 4, we have to calculate and represent the 3 moments created by each force about the axes that we have. Okay, so note in here, I'm going to put that note before. The price you pay when you move forces from one place to another, right, is the moments created by that force about the 3 axes. And in step 4, alright, step 4, what we're gonna do is we're gonna calculate the 3 moments created by each force with respect to the 3 axes and represent them on the cross section. Okay? Calculate the 3 moments created by each force with respect to the 3 axes, with respect to the coordinate system, and represent them, right? And represent them on the cross section. Huh? And how are we going to do that? How are we going to do that? I'll tell you in the next video. The takeaway of this video is, in this chapter we're going to deal with combined loadings, loadings due to double bending, torsion, shear forces, compressive or tensile forces. We're going to see how to calculate stresses at any point on cross sections subjected to these loadings. The main principles that you should always remember is that first, the normal stress at any point is equal to what's happening due to the force, which is plus or minus P over A, depending on whether the force P acts in tension or in compression, and what's happening due to the bending, which is mxy over ix or myx over iy. What's happening due to the shear stress at a certain point is equal to force plus torsion. Force is Vq over it, torsion is T rho over J, where J is the polar moment of inertia. And I gave you an example where the objective was to calculate the stress at any point on this cross section subjected to all of the loadings we have discussed in this course. Alright? And the first step, you're going to be dealing with a 3D problem. The types of questions that you're going to have is a 3D problem where you're going to be asked to find out stresses at certain points on a specified cross section. For example, here you're asked to find the stresses at point A and B on this system, whereby you're having a signal of under the effect of 2 forces. The first step is always, if they didn't specify a coordinate system for you, is you should specify a coordinate system because you're going to work with reference to this system. Step 2 is you're going to draw a cross section with the coordinate system on this section represented. Alright, and step 3 is move all the forces on the system to the cross section that contains the point of interest. Right? In this case, they are A and B because we are interested in calculating the shear and normal stresses in A and B. So how do we do that? We go to the 3D problem. We ask ourselves, is the weight acting in the negative y direction or the positive y direction? Negative y direction. This means it's causing compression. So as if you're moving this arrow, and you're putting it here. okay, which means you are so it's going to be acting in compression, okay, into the page. Now, as if you're moving this arrow, which is F, which is acting in the negative X direction, and you're putting it here in the plane. All right, that's why. Now, we cannot just move forces from one point to another without accounting for the moments they create about the X, Y, and Z axes. How are we going to do that? We're going to see that in the next video. If you have any questions concerning the first 3 steps, please let me know. I will continue in step 4 in the next video.